name's Robert Warren. I've been associated with the JET project basically as a commissioning engineer and safety engineer, originally with the active gas handling system, through to neutral beam heating systems, providing additional power to the JET machine, and now I've started also being involved with the ultimate decommissioning of the facility. When I was working on neutral beam heating systems, the size of some of the equipment is just absolutely massive. When you're using 150 ton cranes and things and lifting 55, 60 ton weight, it's quite impressive, which you might find surprising for a laboratory experiment, as some people think JET was, but I can assure you it isn't. And one of the best memories I've got is to do with lifting out one of the neutral beam heating components, which itself full of water, contained to say about 60 tons. It was radiologically contaminated, and we had to repair some water leaks, which goes into a vacuum space. The idea was it was cut out, welding, all things that lots of engineers like, then had to be repaired to high quality standards, put back into the machine, and then you had to pump a vacuum on the fusion machine. Getting it all right, getting it to work, and such that the physicists could then use this big device. You get the satisfaction of not only the hardware works, it's also the people have made it work. Everyone's come together to get it to work. And if you've been involved in that chain, then you get a buzz out of it. There are unforeseen challenges. You didn't know where the next one was going to come from, as well as some repeat challenges that you knew were going to happen. But basically, you're working in a unique environment. JET is a unique machine. There are similar ones, and there are ones being built, like ITER in the south of France. But the point is, at the time that we were doing it, there wasn't anybody else doing it. So you didn't know what you were going to face with sometimes when you went to a meeting, or when you went to look at the machine, there was something new came along. You've been a supportive organisation to make sure from the point of administration that I can come onto site. I can work with the UKAEA to produce results rather than having to do it all myself. I don't feel like I'm on my own. I do have a parent organisation that I can go to and I can talk to about anything, whether it's just general admin to can you talk to your relevant manager about something to make it work, so we all get the results we want. If somebody else can help take the load away from me as an individual or another individual, then, and they know they've got that, then that's great. I have the comfort when I'm doing the work of knowing that you're there. I got involved in fusion by transferring straight out of nuclear fission. I came down from a place called Dunra in north of Scotland. I transferred from fast reactors in fission to fusion because this JET was preparing for its tritium experiments, and I really wanted a career path in my later career oriented towards fusion, which was still an unsolved mystery. Been going on for a long time, nuclear fusion preparations for it, whereas nuclear fission has been going also for a similar amount of time, but it actually has been producing electricity with nuclear fission power stations. And I felt, well, I've done a lot in that environment, but I think I can do something in this other environment. So I thought a transfer of knowledge, bridging the fission to fusion gap, was very important, and I could sort of hit the ground running, so to speak, in this environment. That's really what drove me at the time, because I was what we call mid-career, or just going into mid-career at that time. There was a few decades left, and what we're going to do with this. And there's a lot more decades left in fusion than just a few decades from where we are now, let alone then. Fusion is not all about theoretical modelling and theoretical laboratory experiments, which was a large part of its history in the past. It's now about practical solutions to the problems, to build what we call hardware essentially in the end power stations to generate electricity. Fusion, there's a large amount of untapped power in nuclear fusion, which we're having a lot of difficulty at the moment in trying to make practically harness to generate electricity. There's a lot of challenges in converting a nuclear fusion reaction to essentially heat to then produce usable power to generate electricity. Power stations know how to generate electricity, but in between that and the actual generators and the actual fusion, such as has been going on at JET, and will happen at ITER in the south of France, there's a bit in between that needs all fixing. And that's where engineers now have a big challenge, which people like myself can help set younger people on based on our previous experience. There are opportunities to learn about practical things. So it will be involving lifting, it will be involving working with vacuum systems, it will be involving working with pressure systems, gas systems, liquid systems. So we've got a wide range of knowledge we require, from process engineers through to physicists, but we need people in between. We need people who can do maintenance, who are maintenance engineers, as I was on power stations. We need them to help get practical things that can be built and maintained when they go into operation. There's the challenges with materials. We're going where we haven't been before. So there's going to be how do you build things out of some interesting materials. There's going to be a lot of taking what I might call university studies and theoretical study we've done in the past, and now test rigs, building the devices, experimentation, yes, but also commission these things. But this time there's something real on the end. Electricity. We need power. We're running out of fossil fuels. We're running out of what we can do. We've got a gap. It's getting wider. But this is a chance to shorten it, and you can be involved with that.